Welcome back. Hi. Energy. Everything's not on fire, it's okay. Yet. We have Dustin, and we're going to learn us some FizzBuzz. Yay!
Hi, everybody. My name's Dustin. I'm DI on GitHub. And I work for a company called PromptWorks, which is a software consultancy in Philadelphia. And this talk is called The Fastest FizzBuzz in the West. But I have to tell you something first. This talk is not actually about FizzBuzz. However, FizzBuzz is kind of the faux motivation for this talk. So in order to get started, I actually, and I can't believe I'm about to say this, I need to explain FizzBuzz to all of you. Because if you don't know FizzBuzz, it's not going to make any sense. So FizzBuzz is kind of this mythical interview question that you might get asked when working on a whiteboard. And the general idea is that you need to write a function that prints the numbers 1 through n. But if the number is divisible by 3, instead of the number, you print fizz. Instead of 5, you would, if the number is divisible by 5, you'd print buzz. And if it's divisible by both 3 and 5, you print FizzBuzz. So I've never actually been asked to do the FizzBuzz problem in an interview for a software job. But at various stages of my career, I've always kind of fantasized what it would be like if someone did. If I was sitting across the table from this guy, and he said, all right, Dustin, let's do FizzBuzz, what would I do? So very early in my career, I'd write something like this. So this basically takes from a range from 1 to n. If it's divisible by 15, prints FizzBuzz, else it prints the number. This is basic FizzBuzz right here. And this would have totally sufficed, right? You run this, and you get 1, 2 fizz, 4 buzz, et cetera, et cetera. But I like to do things a little overkill. So after a little while, I got really interested in very terse programming, and I found this one-liner. And this actually is a perfect implementation of FizzBuzz as well. So I memorized this thing, and I was like, great, if someone asks me FizzBuzz, this is what I'm going to do, and it's really going to blow their mind. But in my imagination, there was never really a limit on what language my solution could be in, right? It didn't have to be Python. I could learn Fortran, and I could do it in Fortran. That would really be funny, right? Or I could learn this language, and this is a valid FizzBuzz implementation too. And I thought maybe I could somehow memorize all that. But I never did. But I was always really curious, and I was intrigued, where could I draw the line in this hypothetical interview question? Could I make my own language and then use it to solve the problem? If I did, I'd call it DIVSPL, which obviously stands for Dustin Ingram's very special programming language. And the #1 priority of this language is going to be able to implement FizzBuzz as quickly as possible. So since it's my own language, I can make the syntax anything I want, right? And I sort of thought, let's make this really simple. Let's make it just the minimum amount of information necessary to encapsulate a certain FizzBuzz problem, right? So the first thing in DIVSPL would be a range of integers that you want to print. And then you have these assignment-like things saying fizz is 3, buzz is 5. And this is it, right? This is what I imagine to be FizzBuzz implementation. So the goal for this talk is to show you how we can take this syntax and actually turn it into something that will solve the FizzBuzz problem. And I have to say that Dr. Vanderplast's talk really showed me that I need to acknowledge my giants. So DIVSPL is built on the shoulder of giants as well, much bigger giants than itself, obviously. So some tools that we're going to use to build DIVSPL is RPLY and RPython. And these are built on other giants, et cetera. Ply, Lex, and Yak, which are, Lex and Yak are old Unix tools that are used to generate lexical analyzers and parser generators. And we'll get to that a little bit later. And real quickly, I want to tell you about RPython, because not everyone is very familiar with what RPython is. It's a restricted subset of Python. So in plain old great normal Python, it's dynamically typed, which means that we can set a variable x, set it to be a string hello, and then later on we can change it to be an integer, and that's totally fine. Python is totally cool with that. And we can do the same thing with functions, right? We can write a function, and in some cases it'll return a string, in other cases it'll return an integer. It's dynamically typed, it doesn't care what it is. RPython, the main restrictions that it gives you is that it's mostly on a limit on the ability to mix types in kind of arbitrary ways. So if we wrote this function in RPython, it would blow up, and it would say a huge error message saying that it's offending annotations, some string and some integer, right? These are incompatible types to return from this function together. So if you see me doing some kind of like weird looking Python stuff later as we get on, this is why. It's because I'm trying to be compatible with RPython's weirdness. So let's design a language, right? And first I want to talk about some parallels to written human language. So let's say that I told you that this is a sentence and I've removed the spaces from it. And I'm going to tell it to you one character at a time, right? So as you're parsing this sentence, you would sort of get one character at a time and you would try to figure out what the end of the sentence is going to be and what the meaning is going to be at the end of it. So you might say I, and then I'll say S, and you say, okay, that's the word is, and you'll go along until you get to the end, and I say, all right, we're done. And you say, all right, this sentence is clearly I saw a man. You sort of can insert those spaces because you have a sort of dictionary in your mind of what are valid English words, like is, awake, saw, man, etc. So if I have a sentence like this, luckily we have spaces, right? I can say, I saw a man eating chicken, and you kind of break this up in your mind into tokens. Tokens being either the words or being the spaces. So you take this stream of characters and you break it up. So you can say, I saw a man eating chicken. And then the next thing that we do is we sort of can group. Now, I'm not a linguist, so this isn't totally accurate and perfect, but we kind of group words together into different expressions. So this is like old school grammar school, right? Like I saw what? I saw a man doing what? Eating chicken. So you can sort of break up the image into these subcategories, and then you evaluate this whole sentence and you get this mental picture in your mind, right? Man eating chicken. But there's sort of an alternative way to parse this sentence also, right? Like what if I grouped man and eating together, and I get a different interpretation of the sentence, and then my mental picture is totally different, right? It's not a man eating chicken, it's a man eating chicken. So luckily we have things like dashes in our language to disambiguate some ways that we can parse sentences. So these are going to be our steps to interpreting a language. The first thing we're going to do is break a stream of characters into tokens. Then we're going to combine these tokens, which would be the letters in the English alphabet, into expressions, like words. And then we're going to evaluate the expressions. So multiple words together are going to give us different mental images, and we bring them all together, we get the final result. So let's look back at my proposed DIVSPL syntax. We have a couple different types of tokens in this language. The first is numbers. So this would be like 1, 15, 3, and 5. And note that I'm saying 15 and not 1 and 5. That's going to be, we're going to consider that one number. We have periods, but I'm going to say that 3 periods after each other is actually the ellipsis token. And we have words like fizz and buzz, and we have the equal symbol. We also have white space, but we're going to ignore it because it doesn't matter here. So let's make a lexer. And the lexer is what is going to take this stream of characters and turn them into tokens in our language. And what it's going to do is give us an iterator that we can call next on, and we can get the new token each time as it consumes some characters from our language. So from RPly, we're going to import a lexer generator, and we're going to initialize it. And then we're going to start adding named regular expressions. So I'm going to say that the ellipsis, and this string is just to name the token. The ellipsis is this regular expression, which is 3 periods separated by 3 periods one after another. Similarly, a number is just going to be any continuous stream of numeric characters. Equal sign is just going to be a regular expression matching the equal sign. A word is any lowercase alphabetic character A through Z, 1 or more times. And because we're really cool, we're going to ignore white space entirely. And we're going to also ignore comments because we're good developers and we'll allow comments in the code. So we'll build our lexer, and then we have this lexer object. And this knows about only the tokens that we've told it. And what we can do with it is we can give it a stream of characters and get an iterator back, and then call next on it and see what tokens it's picked up from this stream. So if I lex the string ... foo42 hut equal sign, I can say next on it and get an ellipsis, call next again and get a word. And so each time it's giving us a token back that matches one of the ones we previously defined. And then the second the second part of the token here is the value. So these are the strings or characters that it's consumed to match that token. Continue, we get number 42. And notice that 42 is a string here because we're just consuming strings still. Word hut. So if our stream has invalid tokens, it continues to work until we need to consume a token that we haven't told our lexer how to analyze. So if I call next on this, we never told it anything about the bang, the exclamation point. So it just blows up. It says, I don't know, this doesn't match any tokens that I know about. So if we give our lexer our entire FizzBuzz FizzBuzz implementation in DIVSPL, it gives us these tokens back, right? And you can see how these correspond. We have a number, ellipsis, a number, and this just goes along until it finishes consuming the whole string, and then we get all of our tokens back out of this. So that's the first part of interpreting a language. We break the characters into tokens, and we're calling this lexing, or using a lexer. The next thing we need to do is combine tokens into expressions. So let's make a parser. The parser is going to take this token stream, so this iterator that it can call next on over and over again, and separate and analyze the tokens according to some set of production rules that we're going to define. But the first thing we need to do is sort of break up some patterns of tokens within our language. So my lovely diagram, this is our implementation. And I'm going to sort of draw some boxes around different expressions in our language. So the first I'm going to call an int box, and these are just integers in the language. We also have a word box. These are just words, and these are sort of the boundaries that encapsulate those tokens. The next is a range box, and this is going to be sort of a combination of tokens, which is an integer, an ellipsis, and another integer. And similarly, we have assignments, which is a word, an equal sign, and integer. And then we're going to have the support for multiple assignments. So assignments box, plural, is going to contain multiple assignments. And then finally, our whole program is going to be wrapped up in what I'll call a main box. And that's going to start with a range box and end with an assignments box. So altogether, it kind of looks crazy like this, but you can sort of see how they nest together. We get what I'll call a parse tree. So at the top, we have a main box, and it contains range and assignments and so on down below it. So let's define our boxes. First, an int box. We're going to implement the base box from RPLY, and we're going to initialize it with a value. And that value is going to be the token that gets sent to this box. So all we need to do is specify a function on this called getInt, and that's going to turn those series of strings which we've consumed into an integer. So all this does is cast value.getString to an integer. So we can use it like this. We give it a token. We give the token to int box. We get a box. We call getIn on it, we get the integer result of that. Range box is going to be somewhat similar. Range box is going to take two int boxes instead, a low and a high, and it's going to return a range. This is just a Python range function, inclusive of these two values. So similarly, we can instantiate a range box, give it two int boxes, and we can call getRange on it, and it will give us a range. Word box is going to be the simplest one. Since they're already strings, we don't need to do anything special with it, and we'll just return the result of getString. And it looks just like this, obviously. Next, we're going to get a little more complex. So the assignments box is going to do kind of a funny thing, and this is what's going to let us implement FizzBuzz with this language. Assignments box, when we encounter that expression in our language, it's going to have an eval_with function, and eval_with is going to be called with an integer. And what it does is something kind of funny. If the integer that it's called with is divisible by the number that it was initialized, it returns, or if it's not divisible, it returns an empty string. If it is divisible, it returns the word that it was initialized with instead. So the behavior kind of looks like this. If we initialize it with a word and an integer, we can eval with a number that is not divisible by 3 and get an empty string back, or we can eval it with a number that is divisible by 3 and we get the word that we assigned to it. So in order to support multiple assignments after another, we sort of have this thing called assignments box, which is plural. And this is, imagine this is kind of like a linked list. You're going to have an assignments box, and this is going to contain a single assignment, and then it's going to point to another list of assignments boxes. So it's sort of like a recursive box in this way. And this is going to have a function called getList on it. So we initialize it with a list of assignments and a single assignment. And getList is going to sort of take this other assignments box, get the list from that, and concatenate it with the single assignment we have. So this is going to basically turn multiple assignments into a list of assignments. So we initialize it like this. We can either say it has no arguments or it has an assignment. And we can call getList on it, and it gives us an assignment singular box back. We can build it up like this. So this is two assignments, one after another, and you can sort of see how they're nested in each other. This gives us the two assignments back. And then the last thing we need to do is the main box. And this is, like I said before, this is the range and the assignments, plural. And this does a slightly more complex thing. So it takes all of the integers in the range, and it goes through all the assignments that it knows about. and it starts to build up a line for each of the integers in the range. And for all the assignments, if we eval it with, we get either an empty string or fizz or buzz or whatever the word for the assignment is back. We append it to line. And at the end, we see if line contains anything or not. If it contains something, that means that that number that we're looking at that particular point in time was divisible by the integer that we're looking at right now. So we append that to lines. Otherwise, we just cast the integer to a string, and that adds the number to lines. So that is a little hard to parse, but if we put it all together, we call a main box with a range and an assignments box, and we call eval on it. We get this string at the bottom that's joined with new lines that looks kind of like FizzBuzz, the output for FizzBuzz. And you can see how that sort of falls into this parse tree here that we showed before. So the next thing we need to do is define production. So this is going to turn a pattern of tokens into one of our boxes. So again, here is our syntax. Thanks. Our productions are going to be like this. Range is going to be a number followed by an ellipsis and a number. Assignment is a word equals number. Assignments plural is an assignment. It's multiple assignments followed by a single assignment, but assignments can also be an empty string. So this allows us to have multiple assignments. And finally, a main is a range followed by multiple assignments. So we're going to instantiate a parser generator from RPLY and tell it about the tokens that we know about. And then we're going to write these productions. So the production is a decorator, takes a string corresponding to the name of the production and number, and returns a box. So here, the number box would return an int box. The number production would return an int box. A word returns a word box. A range is going to have 3 tokens in it, a number, ellipsis, and a number. And we sort of throw the ellipsis away. So we only need to pass the number, each of the numbers to the range box in order for it to work. So range box just takes those 2 arguments. Assignment is similar. Just we throw the equals away in the middle. Assignments plural, we return an assignments box with the multiple assignments and the singular assignment. And finally, we support the empty string by just returning an assignments box with nothing initialized. And then this is the main box, which is the range and the assignments. Okay, so we build our parser, and what we get back is an object that we can pass the token stream from the lexer into the parser. So what we get back from that is the main box, and we can call eval on it and get the string back, the goal of the whole thing. So this is combining tokens into expressions, which we'll call parsing. And the last thing to do is evaluate the expressions. So let's make an interpreter. And this is going to be quick. All this is something that reads a file from the file system as an argument provided to the executable, reads it, takes the token stream, hands it to the lexer. The lexer takes that, hands it to the parser, and we get a result. We call result.eval, and we print it. That's it. That's the interpreter. So let's code. I can write a file, FizzBuzz.DivSpL, that looks like this. I can pip install DivSpL to get executable. And I can say DivSpL, FizzBuzz.DivSpL, there's my output. It works. So let's review real quick. We defined this language, and this produced this set of tokens in order. And then we took those tokens and we handed them to a parser, and it produced this parse tree, all nested in each other. And then we called eval on the result of all of that. And each of them evaled their children until they came out with this result. And then we printed this result to the terminal, and we got this FizzBuzz implementation. So let's take it one step further. If this is the original FizzBuzz problem, where we are checking for divisibility by 3 and 5, what if we wanted to add another problem to it? We wanted to add divisibility by 7 as well, right? In our initial implementation, this would balloon pretty quickly to a lot of multiple cases to support divisibility by 7. But in DivSpL, all I would need to do is change the range to an appropriately large number and add one more assignment at the end, and this works. I can do the same thing. So this will print all the way up to FizzBuzz fuzz. Okay, I have some questions that I was anticipating that I'm going to go ahead and answer for you guys. So the first thing is, why would I ever want to do this? So if you're talking about DivSpL, it's obviously really only good for one thing, which is implementing FizzBuzz. So if you ever meet this guy, make sure that you break it out and show it off to him. But if really your question is, why would I ever want to make my own language, that's a valid question, right? Python is pretty good. Why would I want to make another one? So I didn't really have a great answer to this, but yesterday I was in James's talk, Next Level Testing, and one of his examples, he talks about his tool, JamesPath. And in his talk, I learned two things. First, I learned that this module is called JamesPath, which means he named it after himself, and clearly I will approve of that. But the second thing is that it uses something called a JamesPath expression. So here, it provides an API called search. You can provide a sort of a query and a dictionary, and you get the result from that dictionary. And this is going to get really complex, right? Like he has this thing where you can get the name and sort it and join it with other things. So this is actually like a pretty complex language, this query language for JamesPath. And how do you think he's doing it, right? Like, so if you look at the source for JamesPath, he's got a lexer and a parser in here. Now, he's not using RPLY or ply, and I don't really know enough about it to say if he could, but this is a really great example of when you might want to just make your own language. So here's another question I'm anticipating, is it faster? And again, this kind of depends on what you mean, right? Like, if you mean, is it faster to implement FizzBuzz, then yes, obviously, it's like super short. You could put it in a tweet, it's really tiny. And you still have room for like hashtags and hand claps, right? And by the way, I made our social media guy tweet that, so if you guys go and retweet it, he'd really appreciate it. But if you were here to come to see some like really high performance FizzBuzzing, you might be asking, is it faster to evaluate FizzBuzz? And again, this I think is kind of yes. So as long as you get past the amount of time it takes for our Python to, I don't want to use the word compile, but sort of annotate our program, and ooh, look, it's full of rainbows too. This takes quite a while. This takes like 43 seconds for everything I just showed you guys. But I wrote some benchmarks very unscientifically where I printed FizzBuzz up to 1 million. So this is our naive method, and this is FizzBuzz implementation, and I just ran time like 3 times for each one. And it kind of looks like DIVSPL is a little bit faster. So I'd say, yeah, it's actually faster in both senses of the word. Okay, so I'm about to wrap up. I have some links for you guys. The first is my GitHub, where I have 2 things. I have the full DIVSPL implementation, and it's also on RPytho. And I also have a talks repository, so you can see all the source for this talks, including the proposal that I wrote to get this talk accepted if you're interested in doing your own PyCon talk. And also the PromptWorks website is there. So I want to say thanks to a few people. I want to say thanks to PromptWorks for sending me here and helping me do this work and all my other open source work. I want to say thanks to David Beasley and Alex Gaynor, who are giants and created some of the tools that I use to do this, PyCon staff and volunteers, and also thanks to all of you for coming and listening. I think we have maybe 5 minutes for questions, if anyone has questions.
We have 7 minutes for questions.
7 minutes.
Hi. What does RPython actually do in your example? Is it what interprets and builds parsers or what?
So RPython is a framework for describing languages with Python, basically. So what I use it for here, it's not actually necessary that I do this, make it compatible with RPython, but because RPly is designed to be compatible with RPython, it was sort of an exercise to see if I could do it. And so what it gives us is it allows us to take the Python code that we write and make something a bit like a binary, just an executable that we can run, which is what the DIVSPL command that I was running was. If you're interested in RPython, that's what they use to build PyPy, which is self-hosted Python, and you can look into it. Most people, unless you're designing and writing languages, you're not going to use RPython.
Okay, thanks.
Yeah?
And after you took up the entire interview with the clueless manager who asked you to implement FizzBuzz, did he offer you the job?
Well, like I said, that is a hypothetical situation. So I think if someone asked you FizzBuzz in an interview and you use DIVSPL to solve it, you're probably doing yourself a favor. If they might not hire you. But any other questions? Okay. Thanks, everybody. A company called PromptWorks, which is a software consultancy in Philadelphia. And this talk is called The Fastest FizzBuzz in the West. But I have to tell you something first. This talk is not actually about FizzBuzz. However, FizzBuzz is kind of the like faux motivation for this talk. So in order to get started, I actually, and I can't believe I'm about to say this, I need to explain FizzBuzz to all of you. Because if you don't know FizzBuzz, it's not going to make any sense. So FizzBuzz is kind of this mythical interview question that you might get asked when working on a whiteboard. And the general idea is that you need to write a function that prints the numbers 1 through n. But if the number is divisible by 3, instead of the number, you print fizz.
Welcome back. Hi. Energy. Everything's not on fire, it's okay. Yet. We have Dustin, and we're going to learn us some FizzBuzz. Yay!
Hi, everybody. My name's Dustin. I'm DI on GitHub. And I work for, instead of 5, you would, if the number is divisible by 5, you'd print buzz. And if it's divisible by both 3 and 5, you print FizzBuzz. So I've never actually been asked to do the FizzBuzz problem in an interview for a software job. But at various stages of my career, I've always kind of like fantasized what it would be like if someone did. Like, if I was sitting across the table from this guy, and he said, all right, Dustin, let's do FizzBuzz, what would I do? So very early in my career, I'd write something like this. So this basically takes from a range from 1 to n. If it's divisible by 15, prints FizzBuzz, FizzBuzz, else it prints the number. Or I could learn this language, and this is a valid FizzBuzz implementation too. And I thought maybe I could like somehow memorize all that, but I never did. But I was always really curious, and I was intrigued, like where could I draw the line in this hypothetical interview question? Could I make my own language and then use it to solve the problem? If I did, I'd call it DIVSPL, which obviously stands for Dustin Ingram's very special programming language. And the #1 priority of this language is going to be able to implement FizzBuzz as quickly as possible. So since it's my own language, I can make the syntax like basic FizzBuzz right here. And this would have totally sufficed, right? You run this, and you get 1, 2 fizz, 4 buzz, et cetera, et cetera. But I like to do things a little overkill. So after a little while, I got really interested in very terse programming, and I found this one-liner. And this actually is a perfect implementation of FizzBuzz as well. So I memorized this thing, and I was like, great, if someone asks me FizzBuzz, this is what I'm going to do, and it's really going to blow their mind. But in my imagination, there was never really a limit on what language my solution could be in, right? It didn't have to be Python. I could learn Fortran, and I could do it in Fortran. That would really be funny, right?